Hello, Mr. Cohen. Can you hear me?
I can. Hi, Connor. How are you?
I'm good. Guess I'm okay. I'm trying my best here because I just had finals week for every other class, and my brains have melted a little bit. So I'm gonna be doing the best I can. But what this should be is more of a refresher and a reminder. What I've been doing is going back through the material, and I got to be honest, I brain gap on what I'm looking at as a problem, but when I see the work, it comes back to me.
What have you had since polar and vectors? Have you done any
Nothing.
phonics at all?
Yeah. So there's no new material per se. It's just going back at the beginning of the semester. It's
Okay.
not coming to me when I look at the problem, but when I look at the work, it comes back to me.
Sounds early for you to be doing finals. When are they letting you out for Christmas break?
I mean, after this week is
Really?
it?
Wow.
Yeah. So I mean, I started. I think my first week of class was October or August 14th.
Uh huh.
So it's about it's about 16 weeks, which would about bring it there.
Uh huh. Okay.
So anyway, that's another part of it. I have a little list of things. There are some stuff I want to dive deeper into, but this is mostly just so that I'm on the same page uh, of where I need to be, I guess.
Okay.
So
This
with
is stuff
that being
you can verbalize.
said, the first thing I wanted to ask you about was conversions.
Okay.
This should be pretty simple. I don't think it needs to go into too much detail. If I'm converting from, if I'm converting from, give me a second here. So if I convert from radians to degrees, it's going to be like, for example, let's say it's 3 pi over 8 or something. I don't know if this will work out decent, but let's just say it's that.
What's the conversion factor?
Uh, the conversion factor, I'm not sure if I'm familiar with that term. Are you
Okay.
asking if
The
it's going from
conversion factor is 180 degrees per pi radians.
Okay.
But you
Okay.
can also write that pi radians per 180 degrees. So both of those are the conversion factor, and it depends on whether you're converting radians to degrees or the other way around.
Okay.
Which
Okay.
one would you use for this problem?
So for this one, it's got to be the bottom one because we can cancel or the left one. I'm sorry, because
Yes, because we're
we can
trying to
cancel on the
lose the
bottom top.
radians. In other words, if we were to label this, that would be radians. And so if we
Right.
multiply it by 180 over pi radians, not only does the pi go away, but the radians go away, and we have degrees. And since you're trying to
Okay.
convert it to degrees, you end up with 540 over 8, which is uh,
Can we do? Can
6.
we do 3/8 times 180?
Yes, that's what we're doing.
Okay. Yeah.
And
That.
whatever
Hang on.
that
Give me a
reduces
second.
to, it's not a whole number.
I think you're on the right track. 3 divided by 8 times 180, 67.5.
Yeah.
Is it?
Um, the thing to
Okay.
remember is this conversion factor. And the thing to remember is that it can be either way. And whenever you're converting, you want to lose what you're starting with and gain what you're trying to convert. So if you're trying to
Yes.
turn it into
So
degrees, degrees needs to be in the numerator. If you're trying to turn it into radians, radians needs to be in the numerator. Hold on one second.
there we go. Okay, that's perfect.
Okay. And that's pretty much all it is. There are some quick and dirty methods of converting, but if you, as long as you
No,
use that
that's
conversion ratio, you'll be fine.
Yeah, that was perfect right there. That's that again. That was just a high level reminder. I just
Yep.
blanked when I was doing it.
And
So
that'll
that was
handle
making
whether
sure.
you're going from degrees to radians or radians to degrees.
Okay. Yep. So so the next thing, this is also more of a concept deal, is when I'm finding the reference angle.
Okay.
So relative to say the quadrants, right? Because I want to. There was a question that I had. Let me see if I can go back to
There's
this.
actually two ways to look at this.
Okay.
I don't really use the reference angle. I use what I call the equivalent first quadrant angle, but it always turns out to be the reference angle. In other words, if we take an angle of 150 degrees, well, that reference angle is 30 degrees, is it not?
Right. Yes.
And the formula you use is 180 minus theta. So 180 minus 150 always gives you that reference angle. The
And I
reference
agree with
angle
that.
is defined as the angle made with the x-axis.
Angle made with the x
Yeah,
axis.
let's take another angle.
Yeah. Can you do one in the fourth quarter
I can. Let's do one in
or
the third
quadrant?
quarter
Sorry.
first. Just a second. This is 225.
All right.
So if we want the reference angle, we're looking for the angle that is made with the x-axis, which is this angle. And that you get by doing theta minus 180. So 225 minus
Oh.
180 would give you 45.
Okay.
Okay.
Actually, I think that answered it
Now let's
right
take
there.
one more. In the fourth quadrant, that one's going to be 300. And in the fourth quadrant, it's the same as that, only it's 360 instead of 180. So if our angle is
Okay. Okay.
300,
Okay.
the reference angle is 60. And that is this angle right there. In other words, it's always, the reference angle is always the angle made with the x-axis, not the y-axis. This one is 30, but that's nothing there. That's not referred to anything. Okay? Now, each
Okay.
of these reference angles matches what I call taking an angle and converting it to a first quadrant angle. Because that's what all of these do. In other words, the
Yeah.
180 minus theta converts it to a first quadrant angle. The theta minus 180 converts it to a first quadrant, and the 360 minus theta converts it to a first quadrant. Now, if you're in radians, then this becomes pi minus theta. This becomes theta minus pi.
Minus pi, and that becomes
This
2 pi
becomes
minus
2 pi
theta.
minus theta. So
Yep.
these numbers right here give you the reference angle. They
Yep.
also give you the equivalent first quadrant angle. In other words, in this first case where my angle was 150, the equivalent first quadrant angle is 30 degrees. So if I want the sine of 150, it's the same as the sine of 30 in absolute value. So the sine of 150 would be the same as the sine of 30, and then we put the plus or minus sign on afterwards based on all students take calculus. Because
Okay.
we're in the second quadrant, sine is positive, that's a plus. So the sine of 150
Yep.
truly is exactly the same as the sine of 30. But the cosine wouldn't be. The cosine of 150, its equivalent reference angle is 30, which gives you square root of 3 over 2, But now when we look to its plus minus sign, we're in the second quadrant, cosine is minus. So the cosine of 150 is not the same as the cosine of 30. It's the same absolute value. And that's the way you do it no matter what your angle is. If it's greater than 360, you just subtract as many multiples of 360 as you can. And once you get it below 360, then it's either in the first, second, third, or fourth quadrant. What you're really looking for is the equivalent first quadrant angle, or what is called the reference angle.
Gotcha. Yep, the graph is perfect. The graph is a good visual for me. Okay. So next thing, this I do want to dive in a little deeper. I'm mixing this up with laws of cosine. So this is just solving a right triangle given angles and the side.
Okay. Give me the specifics.
Yeah. Okay. So let's do this one. Angle A, or big A, I guess, is 39.54 degrees.
Why they have to do it this way, I will never know.
Okay.
Why can't they just use 39 degrees? Go ahead.
Okay, and then big C, or angle C, is 90 degrees. And then little b, or side B, is 38.97 meters.
All right, so let's draw a triangle. This is 39. I'm going to round it off regardless because I don't have enough space to write otherwise.
All right, that's fine. We can.
We're going to call this A, B, C. C is 90. So actually, B, we don't need the law of cosines.
B is real simple.
Yeah, B
right,
is 51.
Right. No, this is solving right triangles. That's what I mean, is I'm mixing this up.
So that's little b there. So give me an equation that will give us little b.
Okay, so this is what I'm saying. So for big B, I get it's easy to find the angles because with the right triangle, if they're giving you 2, it's just a matter of subtracting everything from 180.
Actually, I was wrong. You do need the law of cosines on this. Yeah, because we don't have 2 sides. We don't. Oh no, they gave you little b. I didn't put that in.
Yeah, they gave us little b.
Okay, hold on.
Or wait. Yeah, they gave us little b.
Look at it here. 38.97. So we could use pretty much any trig function to calculate both other sides. We'll call that y and we'll call that z. No, excuse me, let's use the same.
Yeah, little a, little b.
Or little a and little c. So let's think about this in terms of trig functions. Because it's a right triangle. Whenever it's a right triangle, you don't need the law of sines or cosines. You need just trig functions. So if I want to figure out little a, which trig function am I going to use? If I want to do it in one step.
So opposite, well, hang on.
You can use sine, cosine, or tangent.
I guess cosine.
Well, yes, you're right. That works. Because I can say the cosine of 39.54 equals little a, equals the adjacent, which is 38.97 over c. Now, that is a number. It's always important to realize that that is a number. And since that's a number and that's a number, we only have one variable here, little c. So it's easy enough to calculate. Multiply both sides by c, divide both sides by cosine.
Okay. Okay.
And that will give you your answer for solving for little c. And then we could use either sine or tangent, or sine or tangent to calculate little a. You also could have used tangent to calculate little a to start with. In other words, you can do these in any order you want.
Okay. Okay.
The key is this. Since that's the one angle we know, let's just say we didn't even figure out that that was 51. We don't need to know that that's 51 particularly. Let's say the only angle we were given was 39.54. Well, now, if I think of it in terms of trig functions of that angle, then I can't calculate much if I used sine, right? If I say the sine of 39 degrees equals a over c, which it does, but I don't know a or c, so now I have two variables, one equation, I can't solve it. So we don't want to use sine as the first step. But we could use either cosine or tangent, because I can say this for the cosine, and I could also use tangent of 39 degrees equals a over 38.97. And that's actually a little faster because your variable ends up in the numerator. So I only have to do one step here. I actually had to do two steps to do that. I had to multiply both sides by c, and then I had to divide both sides by the cosine of 39. But here, a is straight away the tangent of 39 times 38.97.
Okay.
So this is one step. This was actually two steps. So if you're trying to do it as efficiently as possible, you want to do tangent first, and that will solve for little a in one step. And then to solve for little c, you can use any of the three. You can use sine, because now you know a. That's what I would use, would be sine at this point, because a will be in the numerator, and you will have already, actually I would use, it doesn't matter. You could use sine, cosine, either one. You could actually use cosecant and secant also, but those aren't as easily accessible on your calculator. So I tend to solve all right triangles using just sine, cosine, and tangent. And you can do it as long as you have an angle, two angles, and a side. At least you can do it in this problem. Now, for non-right triangles, that's where you need the law of sines and the law of cosines only.
Right.
Never need it for a right triangle.
And I do want to get to those. Let me make sure I've finished all my questions with section or with exam one topics. Yeah,
before I erase this, make sure you understand everything we're doing here.
Yes. Yeah. I don't know why I just totally spaced this. So, but yes, that did fill in the blank.
But that's an important thing: is right triangles. You never need the law of sines or cosines, but you need them frequently on triangles that are not right triangles. Probably every time. I don't even know how to do it without the law of sines and cosines if it's not a right triangle.
Okay, actually, I think we can hop into that with the law of. I know the formulas for law of sines. I just want to make sure. With the law of sines, we always want to solve for the smallest angle first, right?
Not necessarily.
Okay. I know that there's a case where you want to make sure you don't there's a case where you can have
Two
no
triangles.
solutions or two solutions, etc. Yeah.
Yes,
Yeah.
that's
So
right. It's called the ambiguous case for the law of sines.
give
Okay.
me 1 second. Don't get ahead of me. Let me just write that down real quick.
Okay.
Ambiguous.
And that is only going to be when you have side-side angle. It's never going to apply when you have side angle side.
Can you say that again? It only applies to side angle?
You have side angle.
Okay, awesome.
For example, angle A equals 30 degrees. Side A equals 8. And side C equals 10. In other words, if we have a triangle that looks kind of like this, where that's 30, that's 10, and that is 8. Notice we have side, angle. Or angle, side, if you prefer.
Okay.
But this is the only time we have to worry about the ambiguous case. If you have something like this, where you have 10 there and 8 there, hold on. Pi, come on in. Pi, come here. Pi. In this case over here, you actually need the law of cosines, because in order to use the law of sines immediately, you have to have an angle and an opposite side. Notice that in this case I have an angle and I have its opposite side. So I can use the law of sines on that problem. This problem, I don't have that. I do not have an angle and an opposite side. I have an angle, but I don't have its opposite side, and I have two opposite sides, but no angles. So this one requires the law of cosine. And that's the only one that requires the law of cosines, and the other one is where you have side. That requires the law of cosines also. So side angle side and side, both the law of cosines. Law of sines, whenever you have an angle and an opposite side. Pretty much comes down to that.
Side, angle, side.
They almost always give you 3 pieces of information, right?
Right.
They give you an angle and 2 sides, or they give you 2 angles and a side, or they give you 3 sides. If they give you 3 angles, you can't actually solve it, because obviously if they give you 3 angles, I can have a similar triangle. I can have lots of triangles that have the same 3 angles in them.
Yes, okay.
Now, do you want to go through the ambiguous case and how to solve that? I can do it with this example. This is one I've kind of memorized, that this does
that's
ambiguous.
Just, I guess before you get into, let me make sure I've recapped. So the only time we have 2 possible solutions is a side angle, correct?
Yes.
Okay, yeah. So let's keep going.
Okay. So here's how we're going to do this. We're going to use the law of sines, first of all. And I'm going to label it A, B, C. So I'm going to say the sine of 30 degrees over 8 equals the sine of what?
B over little b, which we don't know. And we don't know big B, or
so we
angle
can't
B.
do that one. So let's choose,
and then
choose a side. We know 10.
Okay,
right?
so yeah, so
let's
then
put
10 at the bottom and then sine
C.
C.
Okay. Now, what's going to happen when we solve this is this becomes 1/16, because sine of 30 is 1/2. This becomes the sine of C equals 10/16. You with me?
Yes. Yep.
Okay. So I'm going to go over here on the left. The sine of C equals 5/8. Tell me what C equals.
Okay, so hang on a second. We did 1/2 16ths. So is it 38.6?
You just took the inverse sine of 5/8.
Yes.
38.6.
Yep.
Okay, here's the key step. That is a solution where that is 38.6. We now have all three angles, two sides. Now we use the law of sines to figure out the third side. Okay? However, here is the critical step to determine whether you have an ambiguous case or not. Because you don't always. Just having side-side angle does not make it an ambiguous case. It has to fill certain other requirements. And rather than check those other requirements, the easiest way to do it is to always just figure out the supplemental angle also. What is it in this case?
Oh, okay. So hang on a second.
This is the key step.
38.6. So that's 141.4, I guess.
Now,
yeah.
The question is will that angle fit into that picture? In other words, because the other way this picture might be able to be drawn is this way. Notice that that is still 30, that is still 10,
Yeah.
and that is still 8. So the question is, will it accept a 141.4 degree angle there?
It's possible, right?
Yeah, sure. As long as
because 141 plus 30 is still
30 does not exceed 180, then it is definitely possible. And that's what you do, is you add that to your one given angle, the 30 degrees, and if it comes greater than 180, then you cannot have this triangle. But if it becomes less than 180, then that's a legitimate angle. And this one right up here becomes 8.6 degrees. And this triangle is just as much a solution as this triangle is. It's just a different triangle. But it's got the same first three considerations. It's got the same side angle.
Okay. So obviously side or angle B will be different in both. Is side B going to be the same in each solution set?
No.
Okay. That's
no,
also good.
Yeah,
that makes sense.
This one goes from there to there. This one goes from there to there. So it's going to be much tighter.
Right. Yeah, I'm sorry.
This angle changes and this side changes between the two triangles. Now, let's just for argument's sake say this came out to be 151. Well, that doesn't fit in there. You can't have a 151 degree angle and a 30 degree angle in a triangle. So, there would only be one solution. That's that one. That's how you do it. And then you don't have to remember any of these complicated conditions. There's like 4 of them that tell you whether or not you're going to have an ambiguous case. All you have to use is this test right there. And the main thing to do is your calculator will only give you that. So you kind of have to manually figure out what the supplemental angle is. And because sine is positive in first and second degree, or quadrant, then that sine of that's the same as the sine of that. Exactly the same.
Okay. Duly noted. This is good.
Yeah, this is the part to remember, is actually this part right here, where you add that second.
Yeah.
Add the supplemental
Yeah.
angle.
It makes a lot of sense. It's funny seeing this after 2 months and forgetting. Okay.
Now, it's probably worth us doing one side, side, side.
And this will be a cosine. Cosine.
Yes. 6, 7, 8.
Yes. Okay.
Not a right triangle. I'm going to label it A, B, C. There are 3 laws of cosines. You can use any one you want.
Yep.
We'll start with A squared equals what?
So a squared equals b squared plus c squared minus 2 times a, or no, I'm sorry, times b times c minus cosine, or no, times
Times,
cosine a.
times the cosine of A. Whatever that
Yes.
letter is,
Yes.
that's the letter you need there. In other words, the other versions are b squared equals a squared plus c squared minus 2ac cosine of b.
Quick interjection. My teacher always explains this as wanting to use the biggest angle first so that you get the obtuse angle. Otherwise, you might have an error. Is that ringing a bell or making any sense?
Mm, it doesn't make any sense to me, but maybe I just haven't seen where it causes a problem.
Okay.
I've never done that. I always just pick one at random and begin there.
Okay.
If I'm going to do it the way your teacher, then I want to do b squared because the biggest angle is that one right there, b. And I know that because it's opposite the biggest side. So let's go ahead and use your teachers. It doesn't really matter which one you use.
Okay. Yeah.
You can use any of the 3, and I'm not aware that there's a difference. There might be, just might not be aware of it. So let's
It's
use
something that he
that one.
notes. So
There might be some logic to it. Maybe for an obtuse angle it matters. I don't think so though. So where do we go from here?
okay, so now we start to plug in the
Okay.
data.
Go ahead and tell me the next line.
So that's 8 squared or 64 plus or equals 49.
Yeah, I actually prefer writing it out where you
Okay.
just do pure substitution, just because it's less likely to have mistakes.
Okay, no worries. So yeah, so then 7 times 6 um, times cosine b,
Now, notice in that equation there is only one unknown, cosine b.
or angle. Yeah.
Yeah, and so we can solve this. So what do we have? 64 equals 49 plus 36 minus 84 times cosine of b. That is 85. So that becomes minus 21 equals minus 84 cosine of b. You know, maybe if it's an obtuse angle, you should get a negative answer. Maybe that's why your teacher says that. I'm not sure. But if I go up here, let me change colors. I now have cosine of b equals 1/4. Correct?
Hang on. Yeah.
So
Sorry.
b equals what?
So then inverse of 1/4 is 75.5 degrees.
Now, the way all triangle problems start, or wherever you have to begin by using the law of cosines, the next step is always the law of sines. In other words, you have to use the law of sines in all problems, but sometimes you begin with the law of cosines. notice that because we now have an angle, we now have one angle and an opposite side. Now we can use the law of sines to figure out angle A and C.
Yep. Yep.
I think what your teacher might be referring to is if you had a triangle like this, and this
Okay.
was
Here's a quick explanation online. I don't know if this
uh,
is the same thing, but why do we try to find the largest angle first? The other two angles must be acute or less than 90, and the law of sines will give the correct answers.
correct.
Okay, so that's why he does it.
Yeah, the only difference is that you're going to end up with a cosine of A equals a negative number. But it should be. If that's an obtuse angle, then the cosine of a second degree angle, a second quadrant angle, is negative.
Yeah.
So when you do the math, you will start out discovering that that is an angle greater than 90 degrees. And then, like your teacher says, you use the law of sines for the other two, which are both acute angles. I'm not sure, I don't see why that matters. I bet I can solve this problem starting with angle B without any problems at all.
It's
Something
possible. I
like
mean, I don't, this is just the way he teaches it, and
yeah, yeah, yeah.
I get graded on
I'm
the way
trying
he
to figure
wants to
out
do
if
it.
it makes sense, and I don't think it does. Um, in other words,
If we find the largest
if I
angle,
was
the other
given a
angles must be
triangle with
acute,
these
and the
three
law of sines.
sides, then I would still be able to start with this one, trying to solve for that one. It would be an acute angle. I'd come up with it, and I would use the law of sines after that. Oh, now I kind of see. Because when you use the law of sines to calculate that angle, you get an acute angle, and you have to convert it to an obtuse. So you'd have to use the supplementary angle.
Uh,
Yeah, okay, I can kind of see that. Why it's helpful if you begin with the obtuse angle, if there is one.
okay. Actually, I'm glad you did that. That actually makes
Yeah,
sense
actually,
too.
I'm glad I did it too, because I think I might have learned something. I've never actually tried to solve a triangle that had an obtuse angle and had any problems, but I can see where there is a potential problem.
He always stresses it, so I think because he does that.
Yep.
I'm assuming that's the way he always,
Well,
presents the
that's
problem.
fine. Yeah, there's no problem at all because you can start with any angle you want. So starting always with the obtuse does not hurt you at all. And
Okay.
it does kind of guarantee that you don't have problems in the second and third phase of the problem where you're trying to use the law of sines. Because if you start with the obtuse angle, you will always get a negative because it's the law of cosines. And cosines are negative in the second quadrant, which are all obtuse angles.
So let's switch gears a little
Okay.
bit. I'm hoping to get to two more problems.
Sure.
So this I was hoping to do in tandem. One, it's asking to use the identity to determine the exact value.
Okay.
I did the work and compared it to his solutions, and I just wasn't understanding. So one is sine of pi over 12, and the other is sine of pi over 8. But
And the
the
goal is
difference
to just
here,
find the answer without a calculator? Okay.
exactly. And the difference is he used two different types of identities to do it. And so I just wanted to
Right.
understand why that is the way that is.
Right. Okay. We know the sine of pi over 6, right?
Correct.
Because that's 30 degrees. And if you're going to memorize anything in trig, memorize that the sine of 30 is 1/2.
Okay.
So what this really is if I had the sine, let's see, it's half, so I want to do double. No, I want to do half. I want to do theta over 2, where theta would be 30 degrees. And that will give me the sine of 15 degrees. So when you see an angle that looks like it's half the size of an angle that you know,
Okay.
in other words, this is the same as the sine of pi over 6 divided by 2, correct?
Correct.
So I'm going to represent that as that. Now, what's the identity for sine of theta over 2?
So that's a half angle identity.
Right?
Oh, yeah, okay. I'm sorry. I thought you meant like what the, okay. So anyway, so that's,
Okay, what's the identity?
yeah, give me a second. It lets us use the lookup sheets, so I'd rather do that. So anyway, the half angle identity for sine is plus or minus the square root of all of 1 minus cosine of theta over 2.
Now see, that works because we know that theta here is pi over 6. And I know what the cosine of pi over 6 is. I don't know what the sine of pi over 12 is, but I definitely know what the cosine of pi over 6 is. It's root 3 over 2.
Okay.
Now, since we know it is in the first quadrant, or we're looking at a 15-degree angle, then it's going to be that. And that's how you decide whether it's the plus or the minus. If it was in the third quadrant, in other words, something like 7 pi over 6, that's a third quadrant angle. Well, I know that that has to be negative. So I use that information, knowing which quadrant it's in and what the sign, the plus or minus sign has to be, to choose the plus or minus sign right off. So in this case, it's not plus or minus, it's just the plus.
Yeah, okay.
Okay, and then these usually get simplified to where you have 2 minus root 3 all over 2. That's the numerator. All over 2 again, which makes it like that. And now I can actually take that 4 out, and I have the square root of 2 minus the square root of 3 all over 2.
Okay.
In other words, once you get it to this step, the rest is just kind of complicated algebra. You have to be able to add and subtract fractions, basically. Add, subtract, and divide. And then when you get a 4 that's still inside the square root sign, you can remove that to a 2. And it's always, this is always better than this. In other words, you should always remove any numbers that you can from inside the radical.
Right.
Can't do anything with the 2 or the root 3, but I can certainly do something with the 4. If that was a 5, I wouldn't be able to. I'd just leave it like that.
So actually, this is a perfect example. So let me counterpoint here and explain that he solved this using the difference identity.
You can do that also.
And that ends up being root 6 minus root 2 all over 4. But that is the same as what we have there at the bottom, correct?
Here's the difference identity. In other words, pi over 3 minus pi over 4 is pi over 12. That's going to be 4 pi over 12 minus 3 pi over 12. That's pi over 12. And we know that without a calculator, and we know that without a calculator. So by using the difference instead of the half, maybe it makes it a little easier. I don't know. Not necessarily. But it might, because you probably don't end up with a radical inside a radical, which can be a little confusing, and it may not look like that when we're done. But since we're using the difference formula, we also know that the sine of an angle minus another angle is sine of A cosine of B minus sine of B cosine of A. So you need your basic identity, and then the sine of A, pi over 3 is 60 degrees, that's root 3 over 2. Cosine of B is root 2 over 2 minus the sine of B, root 2 over 2, times the cosine of A, which is 1/2. Okay. Again, everything's first quadrant, so we don't have to worry about a plus or minus sign. And that gives you the square root of 6 over 4 minus the square root of 2 over 4, which is square root of 6 minus square root of 2 all over 4. And believe it or not, that is the same as we got before, even though it doesn't really look like it.
Okay.
That would be a little tough to prove that that's the same exact number as what we had before. I think what we had before was square root of 2 minus the square root of 3 all over 2. If I'm not mistaken. So
I think it was
multiply top and bottom here by 2. And that gives us 4 in the denominator, and it gives us the square root of 4 minus 2 square roots of 3. And somehow that must be equal to the square root of 6 minus the square root of 2. It really, actually it is. You talk about verifying trig identities. It might be harder to verify that this answer is the same as this answer up here. Seriously, it could.
As long as I'm just going to take your word that those are equivalent.
They're the same.
It's just helpful for me to know there's more than one.
And it always happens when you have a choice of two different methods where you can use either the half angle or the sum and difference. They always give you different answers. They're the same number, but they have a great difference in appearance.
Yeah. Okay. So then the last problem, or one of the last problems, I guess depends how much time we take here, but the last section I wanted to go over is the quintessential trig problem, as you've explained it to me.
Okay.
So I don't know if you have an example. I can give you one.
Go ahead. I'll take your example.
Okay. So we have a tangent of 1/2. Or I'm sorry, let me start over. A tangent of theta over 2, so a half identity, but given that the sine of theta equals -2 over 3, and we have a restriction here of 270, where theta is between 270 and 360, or otherwise we're in the fourth quadrant.
Yeah, that's all you really need to know. In other words, these restrictions merely place the quadrant. So we can take that out and say fourth quadrant.
Yeah.
Okay. So what's our first step going to be here? On this,
I guess I would draw a triangle.
Quintessential trig problem. You're right. I have called this that. If you were only going to give one question on a trig test, this would be it, or something similar to this.
Yeah.
They give you They want to know that, and they give you another trig function of theta. And there's always a first step. And if you remember the first step, these come really easy, but you have to remember that first step.
There's two ways you could do this. I guess you could write down, in my mind, what the half angle formula is for tangent, or you could draw the triangle.
Let's draw a triangle. That always works. And it's got to be a right triangle. And you got to label theta. Now notice that theta is between 270 and 360, but we have it as an acute angle here. We're going to handle the quadrant aspect of it later. What we're going to initially figure out is how to dimension this triangle, this right triangle. So what do I do next? That I've drawn a right triangle and I've labeled theta.
Okay, so we've labeled theta, so now we can do the sine, so we can drop.
We can label two sides.
The two sides of sine, I guess. So we have -2. So
actually not. You can't have a -2 as a measurement. So you can only have 2. And where's the 3 go?
So this would be the hypotenuse, correct?
Uh-huh. And now the next step is to always figure out the third dimension.
So in this case now we can do
always the Pythagorean theorem.
Yeah. So everything over square root of 3 squared minus 2 squared.
Which is square root of 5.
Okay.
Okay. So now we have the triangle, and we can go in a number of directions at this point. Let's go ahead and use the half angle formula for tangent. Tell me that its identity.
Okay, so this is, hang on, I'm gonna make sure I have this correct. So everything under the radical of 1 minus cosine over sine of theta. So I'm sorry, cosine of theta and sine of theta.
I think it's this, isn't it? What is
that's one of them. There's 3 variants of this. They're all equivalent. They're all equivalent. So
now, the nice thing about this is that we can look at our triangle to figure out what the cosine of theta is. That's all we have to do, and then we have our answer.
Oh,
then we have to figure out which quadrant it's in to put a plus or minus sign on it. But that's usually the last step, because at this point we're not quite sure what quadrant it's in.
Okay, hang on, give me 1 second. I want to change this to it.
Actually, we are. It's in the second quadrant. In other words, let's go ahead and talk about that for a second, because the rest is just plugging in numbers and doing the algebra here. So this is the quadrant we need to figure out.
Oh.
Not this one.
Gotcha.
We need to figure out where theta over 2 is, as to whether or not to use the plus or the minus sign. So if theta is between 270 and 360, divide everything by 2, and what is theta between? Or what is theta over 2 between?
So that'd be 135 to 180?
To 180. That puts it second quadrant, which means we're going to choose the negative, because tangent is negative in the second quadrant.
Gotcha. Okay.
So we have the negative. We figured that out. Now let's just substitute. What's cosine of theta?
So it's 2?
No, look at this triangle. Tell me what the cosine of theta is.
Opposite.
No, not opposite. It's adjacent over hypotenuse.
So adjacent. So root 5. It's okay. Yeah, root 5.
over 3. And in the denominator,
yes, root 5 over 3.
1 plus root 5 over 3.
Okay.
Is this the right identity for tangent of theta over 2?
It's one of them.
You see the problem I'm going to have here? Ah, no, sorry.
Yeah.
No, we don't. I thought we were going to end up with a negative thing in the radical sign, a negative number, but we don't. The numerator is positive. Root 5 is less than 3. So this number is going to be less than 1. So the numerator will still be positive and the denominator will be positive.
Okay.
Okay. So we can do the algebra. Do you need me to go through it, or can you do the algebra there?
I can do the algebra because
Okay,
we're just
and
going.
just stick a negative sign in front of it because we know we're in the second quadrant.
Right.
But notice that when I drew my triangle, I didn't care about that negative sign right there. I just labeled the triangle with all positive numbers. I still don't care. At no point did I really care about that number. Now, maybe I should have the more I look at it, because cosine is actually negative. Yeah, because the sine of theta is negative, it has to be in the third quadrant, which we know from the original domain restriction. And so when I go to figure out the cosine of theta, that's also in the third quadrant, which is actually negative. So it actually becomes that, and this one becomes negative. And so this would actually be the correct answer. In other words, I can't just read the triangle and figure out what cosine of theta is, because I know theta is in the third quadrant. They told me that. And cosine's negative in the third quadrant. So I have to use the negative answer. I can't just choose all the positive numbers from my triangle here.
Okay.
Okay. It's a subtlety, but it's an important one. Notice that it reversed the numerator and the denominator in our answer.
Yes.
So it's definitely important. You get the wrong answer if you don't do that. So you have to know which quadrant theta is in, therefore to know what cosine of theta is going to be, and you have to know which quadrant theta over 2 is in to figure out what the sine on the tangent is going to be.
Okay. Okay. So let me back up a second because there's something I guess I'm still curious about.
Okay.
So why on the triangle can 2 not be a negative? Because wouldn't that just be like saying y is negative?
I guess it could. In other words, if I made that a negative 2.
Because if we solve for the Pythagorean, it's
but you can't really label a triangle with negative dimensions. There's no such thing as a negative dimension. You can't have a triangle that has a side of negative 2. Turns out that it does solve, no, it actually doesn't solve the problem, because notice that when we go to figure out the cosine, we would still use that over that, and it would look like a positive number, and yet we know we're in the third quadrant, so it has to be negative. So using the negative 2 doesn't really help. If I used a positive 2 and put the negative with the 3, now it would. Now I can take the cosine of theta is going to be root 5 over negative 3, which is correct because we're in the third quadrant. But the sign's actually kind of complicated because I could have put that negative sign with the 2 or I could have put it with the 3, and it matters. So I don't put it with either. I use all positive dimensions. And then just be aware that we are dealing with a theta that is in the third quadrant. And this triangle makes theta look like it is in the first quadrant. So you have to always adjust for where you know theta is and where you know theta over 2 is when you're using this method. I still find this method to be simple and ignore the sign on that -2.
Okay. So let me make sure I understand. So right now, our triangle, although just a picture, our triangle of sine of theta, is in the second quadrant right now, right?
No, it's in the third.
It's in the
Remember,
third.
sine is positive in the second quadrant. So when they tell us that the sine of theta is a negative number, we know it's in the third or the fourth quadrant, one or the other.
Okay.
But ignore it until, because the only purpose of drawing the triangle is so you can label the third dimension.
Yes. Okay.
Whereas this gives me 2 sides of the triangle, and then I always have to use the Pythagorean theorem to figure out the third side. And then I can figure out absolute number values for my cosine of theta. But then I also have to realize that the cosine of theta has to be negative also. So even though I get cosine of theta is √5/3, I know inside that it's negative √5/3.
Okay. Just real quickly.
And that's why that is a plus, because you have 1 minus a minus. And this is a minus because you have 1 plus a minus number.
Okay.
And again, there's probably another way to do this problem other than using the half angle identity. I'm not sure what it would be, but I think you showed me a different way once that will give you an answer that probably does not look anywhere near that. But it will be the same number. Just like the last problem, we could use the half angle or the sum and difference on that one.
Yeah, this one's specifying for the half. I agree. I think there's another way to do it. It's just this one called for particularly. Mr. Cohen, I'm gonna study up tonight. I have till Saturday to take this final. I may borrow another 30 minutes to
have
firm up my
as much time as you want, Connor.
Yeah.
There's a few things I'd rather do than tutor Trig. I love it.
Okay. That's good. That's good.
I'm at your need. I think
I'm just trying to
tomorrow afternoon, and outside of that, I'm pretty open on Friday, Saturday, and Sunday.
Yeah, I got to take it by Saturday. So the latest it would be Saturday.
Your best bet then is going to be tomorrow, probably.
I want to firm up my understanding and identify my gaps, and then I'll go from there. But I'll probably take some more time from you.
Okay.
So
yeah, there's a lot of material here. So
yeah, it's.
I'm sure that your biggest priority is to identify which problems you want to work on.
Right. I mean, yeah, to be frank, I only need to get like a C or better on the final to keep my B. I would need to get like a 95 on the final to get an A. I'm literally
Let's go for that A.
I hear you. I don't want to stress myself out too much. I do want to go for the A. But most importantly, Mr. Cohen, I want to make sure I keep these concepts, and it's not something that just escapes my brain, in a month and a half when I go to calculate.
This is a big step. You use that a lot, where your first step is to draw a right triangle. You use it not only on these quintessential problems, but there's a lot of more difficult problems where sometimes you have to draw 2 triangles because they're talking about 2 different angles. But just remember that when you don't know where to begin, draw a right triangle and label theta.
Okay.
And it's important to label theta, because if I don't label theta, then I cannot dimension that triangle. If I start with just that, I have no idea how to dimension that triangle, because I could label theta up here, and that does change it. That makes that 2, that 3, and that root 5, which is fine. That works just as well. But you have to label theta so you know which angle you're talking about, which of the 2 acute angles.
Right. Okay. Okay, that's great. And I see that you're recording this, so that's awesome.
I am. And
gonna,
did I sent you the link last time?
Yes, I got the last one.
Okay,
I got the last
I'll
one.
send you this one. Actually, I'm not sure if the link that I sent you goes straight to your recording or it just goes to my YouTube channel. But if it just goes to the YouTube channel, then just look for your file name, which is going to always be Connor Meeks with the date 12/10/20. That'll be the file name that'll represent this session. If I
gotcha. Okay.
If your link goes to my channel.
Yeah, there was one part of the last video that I watched as a reminder, a refresher. But anyway, that's perfect. So yeah, I'll just let you know if I'm gonna need more time. Okay. Otherwise, again, thank you as always.
Yeah,
have a good night.
Good luck on your test if we don't have another session, and Merry Christmas to you.
Yeah, thank you.
What are you taking next semester?
I'll be taking Calc 1. So
Great.
I'm almost
the only thing
guaranteed going to be coming back.
Funner than Trig.
I think so, because I asked my teacher and he said that so Calc 1 is, intro to derivatives and getting into derivatives, which sounds like it's more algebra heavy than it is.
It's different. Let me tell you that. It's different.
Yeah. It definitely looks different, but he said if I wanted to prepare for it, I want to firm up my knowledge on college algebra.
Limits are what separates calculus from everything before it.
Okay. He mentioned limits.
You take limits and you combine it with algebra, geometry, and trigonometry, and you have calculus. Without limits, you don't have calculus.
Okay.
That's it. And you have not even dealt with limits, ever.
Nope.
So, limits is really the beginning of calc.
Okay. But yeah, so that's I'm all but guaranteed to keep coming back to you for calculus help, obviously.
Well, good. Glad to hear it.
And if you like calculus even better, that should be even.
I do.
That should be even more beneficial.
Calculus is even more challenging than trig.
Yeah.
And I didn't like it better at first because it was hard, and I was constantly getting questions that I didn't know how to answer, but I've been doing it long enough now that I feel really comfortable with it.
Well, that's perfect, because I'm sure
I'm stumping me.
I'm gonna be trying to get, so before next semester begins, I'm going to be introducing myself to it so that it's not completely alien. But yeah, I'm definitely gonna be getting tutoring help and all that good jazz too. So on that note, Mr. Cohen, I'll let you go. Thank you again.
All right, Connor.
And if I don't talk to you, Merry Christmas as well.
Thank you. Bye-bye.
Bye-bye.